In this video, I'm going to introduce cylindrical coordinates. The idea behind this is to make things easier. In the last video, we encountered a problem with triple integrals that became much easier to complete when we converted from Cartesian coordinates to polar coordinates once we had completed the first integration. And you may have wondered why we didn't just start by looking at the possibility of using polar coordinates from the beginning. But the problem is that polar coordinates are limited to R2 space. But if I could add a coordinate for the height above or below the xy plane, we could extend polar coordinates into R3. This would give me coordinates that look like r theta z for some point P in R3. These coordinates specify a location for my point in terms of r, which gives me a perpendicular distance from the z-axis to my point, theta, which is the polar angle measured counterclockwise from the positive x-axis, and z, which is the signed vertical distance between P and the xy plane. This defines a new coordinate system that we call the cylindrical coordinate system. Examples of what sets of points in cylindrical coordinates look like would include a cylinder centered on the z-axis. In cylindrical coordinates, this has the form the set of all points r theta z such that r is equal to a constant a much simpler form for writing the equation for a cylinder. I could also have a cylindrical shell. A cylindrical shell is a set of all points r theta z such that 0 is less than a, which is less than or equal to r, which is less than or equal to b. I can also give the set of points for a cone in cylindrical coordinates. In cylindrical coordinates, a cone is given by the set of all points r theta z such that z is equal to a constant a times r, provided a is not equal to 0. I can write the equation for a horizontal plane in cylindrical coordinates. A horizontal plane will be the set of all points r theta z such that z is equal to a constant a. I can also specify the set of points that exist in a vertical half plane. This is going to be the set of all points r theta z such that theta is equal to some constant theta naught. So let's work a quick example. I want to identify and sketch points in cylindrical coordinates that are given by the set of all points r theta z such that 0 is less than z, which is less than or equal to 8 minus 2r. Based on the types of sets we just explored for cylindrical coordinates, we know that if z is equal to a times r, we get a cone. But in this case, my coefficient on r is negative, so that the cone here opens downward, and the 8 shifts my cone up vertically by 8 units. The cone also has to lie above the xy plane because of the restriction that 0 is strictly less than z. So that in my xy plane, I have 0 is less than or equal to 8 minus 2r, which gives me r is less than or equal to 4. The projection onto the xy plane is a circle with a radius of 4. This gives me a cone with a base radius of 4 that hovers just above the xy plane and is centered about the z-axis with a peak at the point z is equal to 8 on the z-axis. To convert between rectangular and cylindrical coordinates, we're simply extending what we already did to go from rectangular to polar coordinates. From rectangular to cylindrical, I still have r squared is equal to x squared plus y squared. We still have tangent of theta is equal to y over x, but now we include z is equal to z. To go from cylindrical to rectangular, I still have x is equal to r cosine theta, y is equal to r sine theta, and z is equal to z. So triple integrals in cylindrical coordinates are fairly straightforward once we have a handle on working with polar coordinates. If we let f be continuous over the region defined by d is equal to the set of all points r theta z, such that g of theta is less than or equal to r, which is less than or equal to h of theta, Alpha is less than or equal to theta, which is less than or equal to beta, and capital G of xy is less than or equal to z, which is less than or equal to capital H of xy, then f is integrable over the region D, and the triple integral of f over D in cylindrical coordinates is given by the triple integral over the region D of f of r theta z dv is equal to the integral from alpha to beta of the integral from g of theta to h of theta, of the integral from capital G of r cosine theta r sine theta to capital H of r cosine theta r sine theta, of f of r theta z dz r dr d theta. This triple integral represents the volume of the region in D when my function f inside the integrand is equal to 1. If f describes a density of the object, the triple integral gives me the mass of my object. Let's work an example. I want to evaluate the integral in cylindrical coordinates given by the integral from 0 to 3 of the integral from negative square root of 9 minus y squared to square root of 9 minus y squared, of the integral from 0 to 9 minus 3 times the square root of x squared plus y squared, dz dx dy. In cylindrical coordinates, z equals z, but we need to convert the limits of integration to cylindrical coordinates as well. So that z is equal to 9 minus 3 times the square root of x squared plus y squared gives me z is equal to 9 minus 3r. In cylindrical coordinates, the second integral is for the radius, and the limits of integration for r will go from 0 to 3. And the third integral is for theta, which will go from 0 to pi, because the rectangular coordinates only include the half plane that lies above the x-axis. When I plot this, I have half of a cone centered at the origin with a base with a radius of 3 in the xy plane and a maximum height at z is equal to 9. Now I want to rewrite my iterated integral from Cartesian coordinates into cylindrical coordinates. This gives me the integral from 0 to pi of the integral from 0 to 3 of the integral from 0 to 9 minus 3r of r dz dr d theta. My innermost integral is the integral from 0 to 9 minus 3r of r dz, which is equal to rz evaluated from 0 to 9 minus 3r. This gives me 9r minus 3r squared. My middle integral becomes the integral from 0 to 3 of 9r minus 3r squared dr. This gives me 9 halves r squared minus r cubed evaluated from 0 to 3. I get 81 halves minus 27, which gives me 27 over 2. Now I plug that into my outer integral, and I get the integral from 0 to pi of 27 halves d theta. This gives me 27 halves theta evaluated from 0 to pi, or 27 pi over 2. Let's work another example. I want to find the mass of the solid paraboloid with a density given by the function rho of r theta z is equal to 1 plus z over 9 in the region of D equal to all points r theta z such that 0 is less than or equal to z, which is less than or equal to 9 minus r squared, and 0 is less than or equal to r, which is less than or equal to 3. So that my integral becomes the integral from 0 to 2 pi of the integral from 0 to 3 of the integral from 0 to 9 minus r squared of the quantity 1 plus z over 9 dz r dr d theta. The innermost integral is the integral from 0 to 9 minus r squared of the quantity 1 minus z over 9 dz, which is equal to the quantity z plus z squared over 18 evaluated from 0 to 9 minus r squared. This gives me 9 minus r squared plus the quantity 9 minus r squared squared over 18. I plug that into my middle integral, and I get the integral from 0 to 3 of r times 9 minus r squared plus r times 9 minus r squared quantity squared over 18 dr. This gives me 9 halves r squared minus r to the 4th over 4 plus 1 over 18 times the quantity 9 minus r squared cubed over negative 6 evaluated between 0 and 3. This gives me 81 halves minus 81 fourths minus 0 minus 1 over 108 times 0 minus 9 cubed. This simplifies to 27. so that my final integral becomes the integral from 0 to 2 pi of 27 d theta, which is equal to 54 pi. Now you get to try it. Pause the video and evaluate the integral in cylindrical coordinates. When you are ready, restart the video to check your understanding. You want to evaluate the integral from -3 to 3, of the integral from 0 to the square root of 9 minus x squared, of the integral from 0 to 2, of 1 over the quantity 1 plus x squared plus y squared, dz, dy, dx. The first thing I need to do here is convert to cylindrical coordinates. My integrand becomes 1 over 1 plus r squared. The limits on x tell me we're working with a circle of radius 3, so in cylindrical coordinates my r will go from 0 to 3. The limits on y tell me that we are only working with the top half of the circle in the xy plane, so theta is going to go from 0 to pi. So that my integral in rectangular coordinates becomes an integral in cylindrical coordinates that is given by the integral from 0 to pi of the integral from 0 to 3 of the integral from 0 to 2 of r over the quantity 1 plus r squared dz, dr, d theta. If I sketch this region, I see that I have half of a cylinder with its base in the xy plane and its top at the maximum value for z. I calculate the innermost integral. The integral from 0 to 2 of r over 1 plus r squared dz gives me rz over 1 plus r squared evaluated from 0 to 2. This gives me 2r over 1 plus r squared. Now I put this integrand into my middle integral. I get the integral from 0 to 3 of 2r over 1 plus r squared dr. This is equal to the natural log of the absolute value of 1 plus r squared evaluated from 0 to 3. This gives me the natural log of 10. This becomes the integrand in my outer integral. I get the integral from 0 to pi of the natural log of 10 d theta is equal to theta times the natural log of 10 evaluated from 0 to pi. This gives me pi times the natural log of 10. This is how I can convert from Cartesian coordinates into cylindrical coordinates to make my integration much easier to compute. Let me know if you have any questions.